Thank you. So, I have a background in architecture where I learned how to design and build things for the physical world. I started teaching myself how to write computer code and generating structures in the computer, in the virtual world, sending these parts to robotic machines. This is a 3-axis router cutting 2D parts out of aluminum. And then you take all of these parts, and I would assemble them and exhibit these installations at galleries all over the world. This one was at MIT for the 150th anniversary. It's the Volta-Dom project that I just completed. And so you're probably thinking, wow, that looks super easy, but it's not. And so the problem is, imagine yourself sitting there with thousands of parts, probably looks something like this, thousands of connections, weeks, months on end assembling this thing. You're probably going to get pretty frustrated, and you're probably going to start thinking, God, there's got to be a better way. There's all this information that I use to generate it in code. There's all this information that the machines are using. There's got to be a way these parts can build themselves. So I went back to MIT, and I studied computer science and digital information, self-replicating systems. And now as faculty at MIT, my research is about combining these two worlds. And what I realized is when you slam these two worlds together, the physical world and the digital world, you can literally rewrite what we learned from the Industrial Revolution. And so what I mean by that, so rather than taking raw materials, sending them through a machine or a process that's inherently brute force, that's trying to fight tolerances, efficiency, errors, and try to end up with an end result, the desired end result product. Why don't we take those raw materials, embed some type of information, and allow the materials to build themselves? And that sounds crazy, like Star Trek or something, but that's actually nothing new. All of you right now, your proteins within your body are folding within 10,000 nanoseconds. Your DNA with 3 billion base pairs are replicating roughly an hour. And there's all of these other natural systems. There's a few synthetic examples as well that do this already. They can build far more complex structures. They're far more efficient, lower tolerances. They hardly ever have errors. They replicate. They can repair themselves. It's amazing possibilities in natural systems. So imagine all of the things that we can't build today, or all of the things that we could build if we utilize this technique. And so what I've done is actually broken this down into 4 simple ingredients. So if we want to build structures using self-assembly, we need 4 things. They're really simple. The first is that you need simple sequences of instructions. This is sort of the DNA sequence. So you need to break down whatever complex thing you want to build into simple sequences. Second thing is you need programmable parts. This is sort of like smart joints. You need parts that can take in each one of the steps of that sequence. The third is you need energy, or the muscles. You need something that gets it from point A to point B. So this could be heat, gravity, water, shaking, electricity. The last is you want some type of error correction or protection to make sure that you're going to actually get out what you wanted to get out. So what I'm going to try to do is go through a number of examples. These are simple steps, prototypes that myself and my colleagues at MIT have been working on to go towards the self-assembly future. The first is the Macrobot and Decibot. These were done at Neil Gershenfeld's lab at the Center for Bits and Atoms at MIT. They're large-scale reconfigurable robots. So 8-foot, 12-foot long, essentially proteins. These chains, they're made of electromechanical devices, and they can fold from any one-dimensional to two-dimensional or three-dimensional structure. So large-scale reconfigurable robots. So in this video, you'll see a series of units. They're all the same. It has a string of angles. And those angles, let's say, fold right, left, up, right, right, left. That string is the DNA strand that basically tells it what to make. So it can fold again from any 3D shape to 2D and then back to 1D. And so this is the brilliant team of people that it took. And aside from looking really great in robot helmets, what it actually started telling me was that, wait, there's a problem here. If it took this brilliant team of MIT scientists, engineers, designers to make 8 feet, we're not really getting anywhere. So how can we scale this up? How can it be more passive but have the same functionality? And so what I started working on is a project called Logic Matter. And what Logic Matter does is try to embed all that functionality, but go a step further and actually embed computing. And so literally they're logic bricks. So you take the essential element of a computer, the digital logic gate, and you embed it into a brick. So there's one unit. You plug in 2 units that have faces, input and output faces. And that plug basically reads those instructions and forces you to only make the correct computation. And it's spatial, meaning that the output is either up or down, left or right, depending on where you're in space. So on the left-hand side, if you input a 1, 1, the unit basically forces the correct computation of a 0. This is a NAND gate, or a not and that means it goes down. On the right-hand side, if you input a 0, 0, the computation goes up. So that sounds kind of complex, but imagine you start assembling these things. They're computing, and they're actually building things in 3D space. And so what can we do with that? Imagine we want to build a really, really long straight line. Simple example, extremely straight, extremely long. Well, eventually we're not going to know how much further to go. We're not going to know how much further or how far we've gone. We're not going to know if we've deviated, how far we're off from where we want it to be. So we need parts that could actually tell us some of that. And you could literally set these parts as a counter, a binary counter. So you set the length that you want to go, and as you start building, it incrementally tells you how much further to go. When you get to 0, 0, 0, 0, you know you've gone to the right length. You know that your parts have been assembled, they have discrete connections, so you're accurate and you're at the length that you want. To go a step further, all of the information for that structure is literally built into your parts. So all the blueprints, all the instructions are in your materials. There's no external source. So that means that basically you could walk down the chain, unit by unit, read out your instructions, either a human or a robot, a mechanism, that could read out those instructions and build an exact replica. All the information is embedded in it. Or imagine at small scales, biological structures. Eventually, when we get small enough, we're not going to be able to build machines that are smart enough to be able to build those small-scale, intricate geometries and structures. So what we want to do is build low-level, simple, intelligent pieces that have just enough information that when they combine together, they become a hard drive, reading each other and building the structures they need to build. So you build simple series of computers, basically small bits that can combine and build more complex structures. So the last project is probably the most exciting example that I have of self-assembly, and it's called bias chains. Again, it tries to embed the same possibilities of the reconfigurable robot, but completely passive. So this chain is one unit that you can orient in different directions, and that orientation basically gives it the fold sequence. And that fold sequence, when you give it an energy source, like shaking, it can fold up into any 3D shape. So this example, I have a simple chain, you shake it, and when you shake it, it can fold up into a helix or a spiral. I can fold it, in this case, into 2 cubes. So you can fold 3D structures out of a 1D chain simply by giving it energy. So I basically build the sequence up, I know what I want to get, and I give it some random energy, and it can fold 3D shapes. So, okay, if I haven't totally lost you with all of that nerdiness, let me try to get you a little bit excited about what I think is possible in the future. These are just simple prototypes, but let's talk about where I think this is going. So in this slide, I'm showing you the space elevator. I think it's a great example of a structure that we're going to need to build in the future. Something that's far more complex, far bigger, maybe far smaller, more precise, lower energy. Structures that we can't build today. Structures where we're going to need to find a new process. Or what I think is we're not going to need to find smarter machines, we need to find smarter parts. So literally you have simple parts that can assemble themselves, literally depositing one after another. They can check how well they've done and tell us something about the structure rather than us forcing them to do what we want. The parts are smarter. And I think if you look at disaster relief, let's take Japan. Imagine the ground becomes your energy source. So you have structures that are simple mechanisms like a switch. The beams and columns have a simple state. So when the ground shakes, the structure is literally adapting. It can be more flexible or more rigid based on the dynamic condition. So your structures are actually smart, and they have simple mechanisms that have a state, and the energy source can switch the state. And so imagine any other industry, for that matter, that uses dynamic geometry, the solar industry, let's say, that the geometry could literally adapt on demand as it needed to for optimal conditions, and completely passive. So what I'd like you to do is, whatever industry you're from, energy, solar, space elevators, I'd like you to go back to that industry and actually dare to think about what's possible. How can we get outside of the realm of what we build today, the machines, the process that we build today? How can we build in a smarter way, where our parts are smarter than the machines that actually build it? And I'd urge you to work with me to find new applications. Where can we utilize this? Where can self-assembly solve some of the world's biggest problems? Thank you.